This is Module 13, first video. In this video, we're going to introduce the idea of a best fit line, also referred to as a least squares regression equation. So the idea here in finding a best fit line is that we have a set of observational units, and for each observational unit, we're gathering two quantitative variables. And that means that we're going to be gathering points for each observational unit. We're going to have for each observational unit an input and an output. So our input value is our explanatory variable, and our output value is our response variable. And we will gather these two quantitative variable values from each observational unit. We'll order them so that the input variable is first, the output variable is second, and then we'll have a set of observational units. So for example, suppose I plotted all those points that we got from our sample, and suppose our scatter plot looked like this. In our previous modules, we have learned about the idea of correlation, and I hope you see that the scatter plot I created seems pretty strongly correlated with a line, and you might even draw the line that best fit this scatter plot. It would probably look something like this. That you could all, if I asked everyone in the class to draw that line, you'd all draw a line pretty similar to that. You see when I drew the line, about half the dots are above the line, and about half the dots are below the line. The line that I drew is pretty close to each of those dots. Now, when I draw this line, what I'm really drawing here is what we often refer to as a best fit line. And we're also going to start calling this a least squares regression line, and we'll actually look into a little bit why we call it that shortly. So this line that I have drawn here, the point of drawing it is so that we can use this line, as a model. We can use that line as a model to make predictions about other points that we expect to get if we were to go out and collect more data. So for example, I could use this line to make a prediction about what y value we might get if we plugged in this x value here on the graph. I would take that x value, go up to the line, and say the line would give this point at that x value, and then we could say, oh, well, that is this y value, which would be a good expected, predicted value to get if we plugged in that x. Now, would that be a perfect prediction? No, probably not. I suspect for this particular example that since this line is pretty strongly correlated with that data set, I would suspect that this line gave a pretty good prediction of what the y value would be in reality. Some points to make here about this best fit line. The best fit line for a set of sample data is usually written with this equation, y hat equals b plus mx. From algebra class, you're aware of seeing that the equation of a line can be written in the form y equals mx plus b, where m is the slope of the line, b is the y-intercept of the line, x is the input variable, and y is the output variable. Now notice the similarity here. Instead of writing mx plus b, we just wrote it as b plus mx. All we did was rearrange the way that it's written, just the order. That's it. It's still the same thing though. The number in front of the x is the slope of the line, and the b is the y-intercept of the line. The only other difference I see here is that instead of y equals mx plus b, we wrote it as y hat. But you're familiar with that hat notation. We're saying that it's the sample predicted value of y. We're creating this equation based on our sample data. So this equation is the line that best fits my sample data. So we don't just call it y equals mx plus b. It's y hat equals mx plus b, or y hat equals b plus mx. It is an equation based on my sample. This equation gives us the line that is closest to all the points in my sample data set. This line also gives us the best predicted y hat value for any given x value. And it does remind you here, m is the slope of the line, and that tells us the rate of change, and we'll talk about that more in this unit. It's saying the slope of the line is the pitch of the line, the steepness of the line. And y-intercept, 0, b, tells us where that line hits the y-axis. Again, we'll get into more detail about slope and y-intercept in the next couple of videos. We will use these best fit equations to make predictions about other sample values. So we will use interpolation and extrapolation. Interpolation is when we use our equation of best fit, our model, to make predictions within the span of the given data set. Let me show you what I mean by that. Okay, so here I've drawn another little scatter plot. So my scatter plot is in green, and remember that means the green points are actual observed data points from reality, meaning I went out in the world and I actually observed these points. So for example, maybe I created some sort of test and I went up to each person who took the test. I gathered their age and I gathered how long it took them to finish a test. So as they get older, it looks like it took them less time to take the test. So these green points would be for any particular person, the person's age and their time it took them to take this test. The green points then are what I actually observed in reality. The red line then is this equation of best fit. It's a model. It's a predicting equation that would help me understand if I were to plug in an x value up here, for example, it might predict for me the time it would take that person to take the test. So we could be doing interpolation or we could be doing extrapolation when we are talking about making predictions. Interpolation means we're asking questions and making predictions within the span of the data that was actually observed. So notice the highest x value that was actually observed in reality is about here, and the lowest x value that was actually observed in reality is here. And it looks like the lowest y value observed in reality is here, and the highest y value is here. So that kind of creates this little box, highest and lowest, that traps it all in. Anytime I am making predictions using this prediction equation within this set of x's and this set of y's, anytime I'm using that equation to make predictions in there, that is interpolation. But if I go beyond those x's and y's and I ask to make predictions about reality outside of that span of observed data, that's when I'm doing extrapolation. So if I were to go up here and say, what time do we expect it to take for a person of this age? That would be extrapolation. I'm going beyond the observed reality and asking to extrapolate, to use the equation line of best fit to extrapolate what would happen beyond observed data. All right, the last thing we're going to talk about in this unit is residuals. Okay, so again, I have drawn here another set of data. The data points that we actually observed in reality are in green, and I have drawn an equation line of best fit in red through them. I've purposefully selected two data points that are clearly kind of outliers, one that's very high up here above the line of best fit, and one that seems to be unusually low below the line of best fit. A residual is defined as a y value distance between the observed data set point and the corresponding point on the line of best fit. Go ahead and draw that in orange. So a residual is where you take the y value of your observed data value and you subtract the y value of your predicted value, meaning on your regression line. So the residual for this data point here is the y value of the observed value, which is here, the height of that data point, minus the y value associated with that x value that's actually on the equation of best fit. So this value that is the y value of the point minus the y value of line, is called the residual. So for example, if this were 100 up here and this were 80 down here, the residual would equal 20. Similarly, if we have a data point below the line of best fit, its y value down here maybe is 70. Up here to the y value on the actual line, say that's 90. So the residual is always the value on the point minus the value on the line. So the residual here would be negative 20. So just note then, an overestimate means your regression line is predicting a value that's higher, the observed value, and an underestimate that your regression line is predicting a value that's lower than the observed value. See the next videos where we'll get into some examples of all this.